This is a two-part series on the electrodynamics in tensor notation. So in this part of the series, or in this video, I'm majorly going to be focusing on the four-current density, or also called the current density four-vector. Now, before I start with that, I'm going to first review the four vectors very quickly. Right, so a four vector, right, it's written as A superscript mu, so it's a contravariant vector now. And a four vector is any set of four numbers that transforms as such. So you have this thing is equal to A mu nu on A nu. Now you have to remember that you always sum over the same indices. So we would be summing over nu in this expression, right? And so this is then the transformation, right? And this A mixed tensor, A mu and nu, is the transformation matrix, right? And so likewise now for the covariant and contravariant tensors, let me write it down. T mu nu, which is a covariant tensor, you have the transformation alpha mu, and you have beta nu T. Now we would be having, because this is a covariant, so we would be having in subscript alpha beta, right? So we would be summing over alphas and betas, and we would be getting this thing over here, right? So this is then the transformation for the covariant, and likewise for the contravariant. In contravariant we have these in superscript, so or let me actually write it down with some other letter. Let's call it C, right? Mu nu is equal to the transformation mu alpha and lambda nu beta times, of course we would have C, and it's a contravariant, and so we would be having on top alpha beta, and so again we would be summing over alphas and betas, right? Okay, so let me just write it down that this is for covariant four vector, right? And this is for the contravariant four vector, right? Okay, so now moving on, I'm also going to introduce an operator, right? Let me write it down over here first. Partial sub mu is going to be equal to partial over partial x mu, right? And likewise for the contravariant, partial mu is going to be equal to partial over partial x in the subscript mu, right? And so these two operators also transform as four vectors, right? Now let's see that transformation, right, on some function f. So let's see how would they transform, right? So mu f is equal to partial x alpha over partial x prime mu times partial over partial x alpha and f, right? So we can write it like this, because then this partial x alpha and partial x alpha would cancel out and we would get this thing, right? Okay, so from here then this over here would be the transformation lambda. So we could write this as partial x mu f is going to be equal to lambda alpha mu, and then this thing over here is my, from this, it's my partial mu f, right? Okay, so let me first box this, and over here I said that this thing over here is going to be my lambda alpha mu, right? So let's see why is that like that, right? So let's go on to the next page. Okay, so we know that x prime mu is equal to mu nu x nu, right? So let's perform a contraction that is actually a dot product in tensors. So we are going to do that with this operator over here, right? This vector mixed tensor, actually, this thing. So let's do it, right? X prime mu is equal to, now I would have here alpha mu and again mu nu, and of course my x nu, right? So all I have done over here is in this equation I have contracted it with this over here, right? Okay, so then this right hand side of the equation is then going to be equal to, because these two give me the delta function delta alpha nu, and of course I'd have this thing over here, right? So x nu, right? So then this is then simply equal to my x alpha is then equal to this lambda alpha mu times x prime mu, right? Okay, so then this thing implies that my partial x alpha over partial x prime mu, let me write it down neatly, x prime mu is then equal to my this thing, right? So lambda alpha mu, right? And so I know that this left hand side of this equation I can write it as partial this prime mu is equal to my lambda alpha mu. Now if you say that this thing acts on f, then that would be partial prime mu f is equal to lambda alpha mu on f, right? So this thing over here, right? Okay, so now let's move on and write the covariant and contravariant derivatives in the component forms, right? Okay, so let's go over here and write partial mu is then equal or equivalent to the time component, that is 1 over c times the partial derivative with respect to time, and my partial mu, right? Now remember that this partial subscript t is how I write the time derivative of something, right? And this partial subscript mu is actually, if you go back over here, is this thing over here, right? Okay, so let's go forward, and then this is then simply equal to 1 over c partial time derivative. Now if you look at this quantity over here, this is for the spatial part, and so it's just the derivative, so I can write it as my del operator, right? So this thing over here. Okay, now for the contravariant, I would have mu, and this is then equal to 1 over c partial time derivative and partial contravariant, right? So then this is then 1 over c partial time derivative and negative gradient, right? So that's the relation between the covariant and contravariant spatial components, right? Because the time component in this is positive, and the spatial is all components are negative, right? So now if we take the dot of these two, or say we take this product partial mu partial mu, so covariant and contravariant, contracting these two would then give me partial 0 partial 0. So that's the time component, and all the spatial components would be negative, so partial I partial I. So I is over my spatial components, right? And so then this thing can be simply written as 1 over c squared partial t squared, right? And minus gradient squared. So that's the Laplacian. Now if you remember from my video even on the Klein-Gordon equation, if you have watched that, we define even in that video this thing as our the D'Alembert operator, right? And so we are going to do that over here, but in this tensor notation, then this thing, this contraction of these two gives me this this thing over here, right? And then this was our D'Alembert operator, right? So this squared. So now note that because we are doing in this 4 vector notation, so the D'Alembertian remains covariant in all of the frames, right? Okay, so now let's start. We are actually done with this review on 4 vectors. And so I did it pretty quickly. I hope you have some idea on tensors and 4 vectors already, right? So now let's go to the main part of the video. That is to actually formulate the laws of electrodynamics in tensor notation. But first, in this part of the video, we are going to be focusing on the forecurrent density, right? And so to start off with this formulation of laws of electrodynamics in tensor notation, we must first establish how the sources of fields, that is a rho and j, so the current density, transforms, right? So these two things over here, rho and j. And so then we are going to find out a relation between the two from this forecurrent density, right? Okay, so now we're first going to start off by considering an infinitesimal volume, and we'll call that volume V, right? So let me write these notations down. So V is going to be for the V is the infinitesimal volume which contains a charge Q. So in this small volume, right, there is a charge Q, right? Okay, so and this is moving with velocity V. So velocity, I'm going to represent it with V but with a vector sign on top, so you can differentiate between what's volume and what's the velocity, right? And so then in this case the charge density is defined as rho is equal to charge over volume, right? Okay, and so then the current density would be likewise defined as the charge density times the velocity of the motion of the charge, right? So velocity of the charge, right? Okay, so now we would like to express these in terms of proper charge density that I would call a rho naught. So let me write it down here. So proper charge density is my rho naught, right? Okay, so the density rho naught is then the density in the rest frame of the charge, right? And so then rho naught would be equal to charge q over v naught. So that's the rest volume of this infinitesimal chunk over here, right? Okay, so now we know that the dimension along the path of motion will be Lorentz contracted, right? We know this from special relativity. So there would be some length contraction because the charge would be moving very rapidly, and so for the charge, there would be length contraction in the path of motion, right? Okay, so what that would mean is, if you have watched one of my videos on proper velocity and proper time, so first let me actually write down the length contraction. So this v over here is the volume. So the volume contraction would be written something like this, right? So 1 minus v squared over c squared, and let me get rid of this, yeah, times v naught. So v naught is the volume in the rest frame, right? Okay, so but I know that my rho would be equal to, that was q over v, would now be equal to q over under the root 1 minus v squared over c squared times v naught, right? This quantity over here. So that's my v. But I also know that my v naught, the rest volume, is charge over the rest charge density, right? And so then if I substitute this in this if I substitute this in this equation, right, what I would get is that my rho would then be written as rho naught over under the root 1 minus v squared over c squared, right? So I have simply substituted this value of v naught in this row, right, or in here, right? Okay, so then this is the charge density, and so likewise for the current density, that is J, right, would be, remember that, let's first go back. This is what our J is, right? So J is defined as such, which is the current density. So going back here, let me write it down. Rho times velocity v is then equal to, if you remember, rho was q over v times now velocity v is then equal to, we know what v is, right? Let's go back here. We know that v is this thing over here, right? Okay, so let's substitute that for v. So you would get q over under the root 1 minus v squared, that is again the velocity, right? So that's just the Lorentz factor, c squared times v naught, which is the volume, the rest volume. And of course we will have this v vector, that's the velocity, so that comes over here, right? Okay, and so this is now the charge density, right? Okay, but I know that, let's go back here, sorry. Yeah, from this equation, I know I can write my rho naught as rho over this quantity, right? So then I can write my current density as being equal to rho naught times v, the velocity, over under the root 1 minus v squared over c squared. right? And also know that my rho is gamma times rho naught, right? So that's the transformation from a rest frame to the moving frame, right? Okay, so now we can write this thing in 4-vector notation, and note that this part over here is my proper velocity, right? So if you have watched the video on the proper velocity and proper time, you would know this, right? And so then in 4 vectors I can or I'll go on to the next page, or let me actually write it down over here, right? So J mu would be equal to rho naught eta mu. Now this eta mu is my proper velocity, right? So it's in 4-vector notation, and rho naught is again my rest charge density, and then I have this J mu over here. This J mu is actually called the forecurrent density, right? So let me go and write down its time component as well. So I'll go on to the next page, and let me write down my time component. That would be J0 is equal to rho naught times eta 0, right? So this is now the time component of this. Let me actually box this thing, right? Okay, so all I have done is substituted for mu being equal to 0, and so I got this thing. But I know that my let me write it down here, that my eta 0, or the time component of the proper velocity, is then my c over under the root. I have this 1 over under root 1 minus v squared over c squared, because of the fact that we are talking about proper velocity, right? So the time component is c over this factor over here, right? So then I can write the time component of my current density as rho naught c over under the root 1 minus v squared over c squared, right? And we know that rho over under the root of 1 minus v squared over c squared is then just rho, right? We know that from this thing over here, right? So then I can again write this as c times rho. So the time component, we can see, is then simply the charge density, right? So let me write it down. J0, the time component of the forecurrent density vector, is then simply my charge density, right? This thing. Okay, so I can then write it for the spatial components as Ji is equal to rho naught times eta I, right? And so in general, including the time components and the spatial components, my J mu is then equal to, let me write down, first I'd have my time component, that was c times rho, and the spatial components would be simply jx, jy, and jz, right? So here the spatial components are of the ordinary current density, right? And the time component is my charge density. Now again, this quantity J mu is then called the forecurrent density, right? And now let me just quickly go over the physical interpretation of this, of the forecurrent, right? So it says that the charges at rest will appear to remain at the same spatial position for some interval of time, right? So that is, they do not move, or they're stationary. So when they do move, then that corresponds to changes in position, obviously, and therefore the charges have velocity, right? So the charges will move and they will have some velocity, and the motion of the charge constitutes an electric current, right? So we know that when charges move, there is some electric current, right? And so then this means that the charge density is related to time, while the current density is related to space. And we can see that from this equation or this expression over here, right? So the time component is related to the charge density, and the spatial components are the current density, the ordinary current density components, right? And so the forecurrent actually unifies the charge density, which is again related to electricity, and the current density, which is related to magnetism, in one electromagnetic entity, right? Okay, so let me also mention some of its usages or uses in it is used in general relativity and quantum field theory as well. So in general relativity, the forecurrent is defined as the divergence of the electromagnetic displacement, right? And in quantum field theory, the forecurrent density of charge is actually a very important component of the Lagrangian density that is used in the quantum electrodynamics, right? So that's not the scope for this video. We are actually done with defining the current, or the current forecurrent density, right? Now let's move on and recall that we have a continuity equation, right? So recall the continuity equation, that is del J, or the divergence of J, is equal to negative partial time derivative of the charge density. What this equation briefly means or says is that if a charge is moving out of some differential volume, then the amount of charge within that volume is going to decrease, right? And so the rate of change of charge density is negative, right? So that's why we have this negative sign over here, right? Okay, so we would be expressing the local conservation of charge as, let me write it down here, del dot J is equal to the x derivative partial x of my jx plus partial y jy is, sorry, plus partial z jz, right? So I've simply just expanded this thing over here, and so this would then be equal to sum over I of my partial xi ji, right? And of course this would be going up to 3. So right, okay, so then we have this thing, partial t of charge density is equal to negative 1 over c times the time derivative of this thing over here, right? So this thing actually obviously comes from the continuity equation, and then all I have done is written my rho in terms of j, right? So we knew that the zeroth component of J, the current density was it was C times rho, right? So then well, coming back to this, then this is then equal to negative partial the x derivative 0 j0, right? So we are talking about the time component right now. Again, this thing also comes from this continuity equation over here, right? So this thing is for the partial derivative with respect to the coordinates, right, which is on the right hand side over here, sorry, over here, right? Okay, so with this then what I can say is that my partial x0 j0 is equal to negative partial xi j I, right? So the simply the time component is equal to the negative of my spatial components, right? Again, mentioning that this comes from over here, right? Okay, so what this means is then the sum of these two would be 0, right? So plus partial xi j I, and this over here is equal to 0, and this implies that then I can shortly write this as partial mu j mu is equal to 0, and this now is the four-dimensional divergence of the four-current density. And so the continuity states that the four-current density is divergenceless, right? So what that means, or what that implies, is that implies the charge conservation, right? So the statement of charge conservation is that the Lorentz invariant divergence of J is 0, right? So it's divergenceless. Right, okay, so we are done for this video for the deriving or writing the four current density. In the next video, I will be briefly going over the Maxwell's equations, and then we are going to write them down in the tensor notation, and we would be deriving the field strength tensor, the electromagnetic field strength tensor, and then its dual field strength tensor, and we would be seeing how that helps us in writing or deriving the Maxwell's equations, right? So that's it for this video. I hope you understood the concept of the four current and the usage of special relativity in electrodynamics, and that it is compatible, the electrodynamics is compatible with special relativity.